Hello, everyone. I'm Farzad Shahabi from Habits Lab at Northwestern University Department of Preventive Medicine. In this presentation, I'm going to talk about our paper titled ActiveSense, a novel active learning framework for human activity recognition. Data annotation is not easy. With the advent of portable and wearable devices, such as mobile phones and smartwatches, users easily create large amounts of sensory data every day. One important challenge in building machine learning models for mHealth applications of fine-grained activity is the generation of accurate annotations with well-defined start and end time labels. However, labeling large amounts of unlabeled data is, on one hand, expensive and time-consuming, and on the other hand, it's error-prone due to task intensiveness. Also, it's not clear whether labeling all the data is even necessary to building the most effective machine learning model. Annotators waste time labeling redundant and irrelevant instances containing minimal information for a machine learning system. So, smarter strategies are needed to minimize data annotation. Active learning or human-in-the-loop machine learning is one of them. In general, there are three types of selective query strategies within active learning. First, pool-based sampling. Second, stream-based sampling. And third, membership query synthesis. Pool-based queries strategy, which we see on figure on the right side, help minimize the data annotation effort by adaptively selecting a subset of samples, which is called query budget, from the unlabeled pool in each querying iteration. These candidate samples are designed to be maximally informative to the machine learning model, which intuitively leads to improvements in classification decision boundaries, leading to selecting informative samples in each query. Membership query synthesis algorithm generates data instances from a certain underlying distribution, and the labeler is then asked to annotate. In the stream-based sampling scenario, samples are generated sequentially in an online or real-time setting, and a decision needs to be made in real time, whether this sample should be labeled. Uncertainty sampling is most widely adopted within each of these methods. An uncertainty metric needs to be defined to determine data samples or segments for which the model is least certain in its decision and prioritize them for annotation and training. Maximum entropy is most used method to measure model uncertainty. We evaluate our active learning framework on the Nexus free living dataset. Let's introduce Nexus free living dataset briefly. Nexus free living dataset is obtained from 10 participants with and without obesity in a naturalistic setting with the goal of detecting eating behavior. More than 137 hours of data is collected by a multi-sensor necklace worn around the neck throughout the day. It has a proximity sensor to capture chewing actions occurring during an eating episode. It has an IMU sensor to capture motion and ambient light sensor to capture leaning forward. The device captures periodicity in the chewing signal when oriented towards the jaw. The candidate segments for classification are obtained from the proximity sensor. It contains around 123,000 candidate segments, which is 9.4 of the segments correspond to actual chews and 90.6 correspond to non-chews. In this slide, I will talk about uncertainty visualization for Nexus data through data map. Data map visualization generates three different statistics: confidence, variability, and correctness, obtained from the training phase of a deep neural network across multiple epochs. We assume that the model predicts a probability distribution across all classes and data instances over epochs. Confidence is defined as the average model's confidence of a data instance across different epochs. Intuitively, a higher confidence value for an instance means the sample is easier to learn from the model's perspective. Variability is another statistic defining model's confidence variation in predicting one instance with respect to ground truth over epochs. Correctness is another statistic measured by the number of times the model has predicted the sample correctly across different epochs. The figure shows how Nexus instances are scattered based on the three different training statistics. We can see that the trained set is decomposed into easy to learn and hard to learn regions. Most of the data instances are easy to learn, with high confidence and low variability in the top left of the figure. The bottom left of the figure corresponds to hard to learn region. It contains instances with low confidence and low variability. Easy to learn samples play an important role in model convergence and learning, while hard to learn instances are needed for the model's robustness and generalizability. Note that uncertainty sampling strategies utilizing metrics, for example, entropy, choose instances with highest variability and confidence from the data during the training phase, since it implies the model's indecisiveness about these samples. In this slide, we will talk about the area under the margin statistic. Place et al. Introduced the concept of area under the margin statistic to identify mislabeled samples. We repurpose AUM to determine samples with intrinsic uncertainty. AUM is the mean difference across all epochs between logit Z of I of the ground truth subtracted by the largest other assigned logit, max of Zij, which I is not equal to j. Logit value is the pre-softmax output of the final layer of the deep neural network. This representation allows us to have another measure to identify hard and easy samples. We modified the AUM statistic to suit the unsupervised setting by taking the absolute value of the M of X and Y, since the ground truth of Z of J is not known prior to labeling, which will allow us to find the samples with intrinsic uncertainty, low quality samples. In this slide, we want to show the AUM distribution for the segments obtained from hard and easy chewing intervals. Figure on the left shows an easy to learn chewing signal in red that has a visually higher quality chewing interval, where peaks in the proximity signal are distinct and represent periodicity in jaw. Hard to learn signal in blue on the left reaches proximity sensor saturation at some points and does not follow a normal chewing pattern. Figure on the right shows that the AUM values distribution for the segments of two hard to learn and easy to learn chewing intervals. The AUM model could determine that harder to learn chewing segment follow a distribution with a lower mean of 5.3 compared with the easy to learn interval with a mean of 25.23. This slide is showing the uncertainty visualization for the segments of easy to learn and hard to learn chewing intervals. It can be inferred from this slide and the previous slide that lower values in AUM distribution are translated to lower model confidence and higher sample ambiguity, which we visually confirmed earlier. This slide shows the pipeline for cluster-based maximum entropy as an already existed active learning method. The figure shows how a traditional active learning method, for example, cluster-based maximum entropy, would work. A cluster-based active learning algorithm would first perform clustering on the unlabeled batch of data to account for diversity sampling. In each querying iteration, the active learning algorithm picks a subset of samples called the query budget alpha from the unlabeled batch of data as labeling candidates nominated to be labeled and identified with respect to the existing class labels by the annotator. The labeled batch then is updated by the newly labeled instances. Samples selected by active learning algorithms like maximum entropy tend to account for model uncertainty due to significant changes in decision boundaries, which translates to high variability in data map. In this slide, we talk about our proposed active learning framework. Similar active learning approaches, for example, cluster-based maximum entropy, is utilized to consider model uncertainty. Clustering is done to account for sampling diversity. However, to cast a wider confidence net, we increase the querying budget to beta, which is much more than alpha. An AUM filter is added to select the alpha samples with least AUM values, considered harder to learn with lower confidence. The AUM statistic provides the desired filtering approach combined with uncertainty sampling using cluster-based maximum entropy to represent and account for the model and intrinsic uncertainty. The figure shows in this slide the results for cluster-based maximum entropy, which is CME only, AUM only, CME plus AUM, which is our proposed method, and random sampling, and compares them with the best evaluation used in Nexus dataset. Best evaluation is considered the results using the whole training set. We can see that our proposed method outperforms other approaches and reaches the best evaluation performance after 12 query iterations, which is equivalent to 0.18% of the unlabeled data. However, cluster-based maximum entropy, CME, reaches the performance of best evaluation after 30 iterations, equivalent to 0.29% of the data, performing better than random sampling and even also AUM only. AUM only approach picks least AUM values from the unlabeled pool as candidates for annotation. In conclusion, we proposed a new active learning framework which harnesses intrinsic uncertainty as well as model uncertainty. We also show how the AUM statistic, originally designed to detect mislabeled data, can be repurposed to capture segments that are easy and hard to learn without the need for ground truth labels. We show the proposed method achieves best evaluation performance when using 0.15% of the data compared to 85% of the data in the best evaluation method. Future research should look into ways of reducing training time and test our proposed method on other real-world datasets. We would like to acknowledge the support we are given by NSF and NIDDK in this work. Thanks to the co-authors and to the great team behind this work, and now we will be open to your questions, comments, and feedbacks. Thank you very much.